Hello everyone, welcome to my channel Physics with Sebbi. Here I came with amazing problem but simple one. First I will read it. A tumbler toy is placed on the top of a fixed ball of radius R. The lower surface of the toy is a hemisphere of radius r. The center of gravity of the toy, point C, is located at half of the radius of the hemisphere. Will it fall off the sphere? The condition given is there is no slipping. Please pause the video and give it a try to solve it. Here what it is given, now come to the solution. Here what it is given, this is the toy in the shape of hemisphere whose radius is smaller. C point is center of gravity. From the center of curvature to the center of gravity, the distance is r/2. And this is the fixed sphere whose radius is capital R. What is the question? When this hemisphere is kept on this top of the fixed sphere, will it fall or not? That we have to decide. This is the initial condition. After some time it rolls like this. After some time further it rolls. Means suppose if the body rolls like this, if the toy rolls like this, whether it comes back or not. If it comes back, then we can say that it will stay on the fixed sphere. If it doesn't come back, then we can say that it will fall off. Here you see this is line of symmetry. In the first figure also, this is the line of symmetry. Okay, now come to the solution. O is the center of the fixed sphere. O1 is the center of curvature of the hemisphere. Only you have to take here half. The remaining just I completed, but you have to take only up to half. Okay, O1 is center of curvature of the hemisphere. O is center of the sphere, fixed sphere. And this line, this blue line, line of symmetry in the initial position of the toy. And this is also line of symmetry in the final position of the hemisphere. And this line, this green line is the line joining the centers O1. Okay, to calculate the condition of the stability, we require these lines. That's why we imagine. Okay, where C is the center of gravity, which is at a distance r/2 from this O1. Draw one perpendicular line AB from the point of contact A in the rolled position. Here point C is to the left of vertical AB line. Then automatically this hemisphere will come on to the equilibrium position. Why? The center of gravity here to the left of AB, therefore moment of center of gravity with respect to the point A, with respect to the contact point, will move this hemisphere to the original position, to the equilibrium position in counterclockwise direction. Suppose this point C is to the right of vertical AB line, then what happens? The moment of C about the contact point will move in the clockwise direction. Due to that, the hemisphere will fall down. Means if C is to the left, then the hemisphere will come to the original position and it will be stable. If C is to the right of AB, it will not stable. The hemisphere will not stable. Means what? This length CO1 should be greater than BO1. That is the condition of equilibrium. Means the length of O1C should be greater than the length of O1B. O1B. Here, that I write here. O1C should be greater than O1B. Then what happens? The C should be to the left of AB line. So this hemisphere come to this original position, means equilibrium position. O1C is given in the problem, that that's value is R by 2, and O1B that we have to find out. To find out O1B, we assume all these things. With the line of symmetry, with the initial line of symmetry, the line joining the centers makes an angle beta, and the line of symmetry in the rolled position makes an angle alpha with this line joining the two centers. Means here the angle is alpha, here the angle is beta, and A is the contact point. Then what happens? Now you see here, in the triangle ABO1, in this triangle, at point A, the angle is beta. Because here the angle is beta, therefore this angle is also beta. Because this line and this line, parallel lines, this is line of transversal. If the angle is beta, here the angle is also beta. Now this angle is alpha. Inside the triangle at O1, the angle is alpha. At point B, inside the triangle, the angle is pi minus alpha minus beta. For this triangle, we require BO1 length that we have to find out. But we know that AO1 as R, and angles also unknown. Therefore, relating BO1 and AO1, we can write the sine rule. When we apply the sine law for this triangle ABO1, we will get like this, isn't it? Here this value is written as B is equal to alpha into R by R. We have to find out that. Why I am writing B is equal to alpha into R by R? For this, what we have to do is, when the hemisphere come to the rolled position, on the sphere this length is contact length. What is that? EA. EA length is contact length for the sphere. When the toy rolls from initial position to rolled position, this length DA is nothing but contact length for the hemisphere. When the hemisphere rolls from initial position to the rolled position, means to the new position, when it comes like this, the two contact lengths must be equal. Means EA should be equal to AD. That I am writing here. Here you see EA. EA is nothing but R beta, and AD is nothing but R alpha. This angle is alpha and this radius is R. Therefore, DA length is R alpha and EA length is R beta. these two contact lengths are equal, means here you see R alpha is equal to R beta. From here I can write beta is equal to alpha into R by capital R. This beta I used in this sine rule. Where is that? Here. I apply the sine rule. R by sine alpha plus beta. Take alpha as common. Then 1 plus R by R by substituting beta value. Okay, we will get like this. But here when is we have to take the rolled position for a small angle of beta. Then what happens? Sine beta is equal to beta and sine alpha into something is equal to alpha into something. From here I can find out O1b as R square by R plus R. This O1b value we have to substitute in this equilibrium condition. O1c is nothing but half R, which is greater than O1b. O1b we obtained as R square by R plus R. From here we get a great result. Capital R should be greater than small r. Capital R should be greater than small r. Means what? The radius of the hemisphere must be less than the radius of the fixed sphere. Okay, this is the solution. Next time I will come with another amazing problem. Until then, goodbye. But please subscribe my channel, press bell icon and share it.